equation. Let me just show you what I have in mind over here. Suppose I tell you that y is a twice differentiable function of x that satisfies the following identity, that the second derivative of y with respect to x minus 5 times the first derivative of y with respect to x plus 6 times y is identically 0. And the question is, if this equation is to be obeyed, what must y be? And a very interesting technique for solving this kind of a problem. You see, this is called a second-order differential equation because the highest derivative that appears is the second derivative. Okay? A rather powerful technique using the exponential is available to us for problems of this sort. And the idea hinges on this. As a trial solution, which I'll call y sub t, let's try e to the rx, where r happens to be a constant. You see, the whole idea is, if I differentiate e to the rx with respect to x, I get e to the rx back again, only with a factor of r, namely the derivative of my exponent in this case. See, r is a constant. The derivative of rx with respect to x is just r. So notice that the first derivative of y sub t with respect to x is r e to the rx. The second derivative of y sub t with respect to x is what? R is a constant. I differentiate e to the rx. That brings down another factor of r and leaves me with e to the rx. You see, the whole idea being, notice that e to the rx is a common factor of y sub t prime, y sub t double prime. If I now substitute these results back into my original equation, look what I wind up with. Y double prime becomes r squared e to the rx, minus 5y prime, that's minus 5r e to the rx, plus 6y, 6e to the rx, and that must equal 0. And here's the key point. E to the rx is now a common factor. I factor that out. Okay? If the product of two numbers is 0, one of the factors must be 0. But notice from our graph of the exponential, the inverse logarithm, e to the x, e to the rx can never be negative, and can never be 0. In fact, e to the rx is always positive. Therefore, if e to the rx is always positive, it must be the other factor, which is 0. But r squared minus 5r plus 6 is not a second-order differential equation. It's a second-degree polynomial equation. It's a familiar quadratic equation, which I can solve quite easily. In other words, I find what? That r must be either 2 or r must equal 3. In other words, my claim is that either e to the 2x or e to the 3x must be a solution of this particular equation. Of course, we can do more with that, which we will in a later part of calculus, not in this package's work, but we're not going to study differential equations in great detail here. But for our present purposes, I think this illustrates how one can use the fact that it's a rather powerful structural property when the derivative of a function with respect to x is the function itself. By the way, as a quick check, notice that if y equals e to the 2x, y prime is twice e to the 2x, y double prime is 4 e to the 2x, and therefore y double prime minus 5y prime plus 6y is what? It's 4 e to the 2x minus 10 e to the 2x plus 6 e to the 2x, and that, in fact, is genuinely identically 0. In a similar way, checking out y equals e to the 3x, we get y prime is 3 e to the 3x, y double prime is 9 e to the 3x. Therefore, 9 e to the 3x minus 15 e to the 3x plus 6 e to the 3x is again identically 0. And again, you see what this powerful technique is. In general, if a and b are constants, the substitution y sub t equals e to the rx, and there'll be a problem in the exercises on this to give you additional drill. But that substitution transforms the second-order differential equation y double prime plus ay prime plus by equals 0 into an equivalent quadratic equation r squared plus ar plus b equals 0. And you see from this equation, using the quadratic formula, we can find the values of r that satisfy this, and that gives us a couple of solutions to the equation. Well, at any rate, I deliberately want this lecture to stay short to make the most important impact. And that is, again, what? that once we knew what the natural log function was and we defined the inverse natural log function, everything that we wanted to know about the inverse natural log followed from the properties of the log itself. And this is basically the lesson for today. We will continue the discussion of exponential functions from a different point of view in our next lecture, but until that next lecture, goodbye.
Funding for the publication of this video was provided by the Gabriella and Paul Rosenbaum Foundation. Help OCW continue to provide free and open access to MIT courses by making a donation at